Welcome to the Grain Farmers of Ontario GrainTalk webinar, focusing on drift management. I'm Laura Ferrier and from Grain Farmers of Ontario, and today I am joined with Dr. Jason Deveau. Jason is an application technology specialist with OMAFRA. He's based out of the Simcoe region at the Simcoe Resource Centre since 2008. Jason is one of my most favorite speakers that I hear talk on spraying and application technology and everything else. So I'm so excited to have him join us today. One quick housekeeping item for those of you who are looking for CCA CEU credits, there will be an opportunity to earn them later on in this video. Thank you, Jason, so much for joining us for this webinar on drift management, and I will turn it over to you.
Thanks, Laura. I'm heavily caffeinated. I'm going to try to turn what I think all of us know is kind of not the nicest subject, not the most interesting subject, something I hope is a little more interesting. So let's just jump right in. Let's start with talking about off-target pesticide movement. Bit of a broader term than maybe you were thinking of. So I want to explain a little bit about all the sources of off-target contamination because we tend to focus just on drift. That being said, let's start there. One source of off-target contamination or pesticide going where we don't want it to go is through the air. That's drift. That can either come directly off the nozzles or it can lift off sprayed surfaces. But there are other ways product can move where we don't want it to go, and they should be mentioned. One is point source, and that's any product that comes from on your equipment or from out of your equipment. It could be leaky storage, it could be carryover in your sprayer, or in your tender systems. It could be spills, however small, when you're filling. It could be, what do you do with your rinseate? Oh, we just make that go away during cleaning, or even priming the boom, which tends to take place at the entry of a field over and over and over again. There are also environmental sources of pesticide movement, which are a little more subtle, but they exist. This tends to happen long after you've gone home. One is surface runoff. Maybe rain moved a water-soluble product along the surface of the water into a water course, or maybe it ended up in the water table. And there's atmospheric kinds of pesticide movement. These are really insidious. This is product that goes up into the atmosphere, hangs out there for a while, and then recirculates in precipitation. Even contaminated dust blowing off a field is a source of contamination. But we can't tackle all of this today, so we will focus on drift. There are, it may come to surprise you, two different kinds of drift. And I'm going to use some of the larger, more scientific terms here because it makes me seem impressive. The first is primary movement. This is the one we all kind of intuitively understand. It is the initial mechanical drift of droplets, and it's caused by turbulent conditions or mechanical conditions. Wind is often the culprit. Then there's a secondary form of drift or secondary movement. This happens maybe a little later. This is a delayed and maybe even prolonged form of drift. And it's less to do with what an operator does and more about the chemistry itself. The molecular structure of the product you applied may or may not lend itself to volatilizing and lifting off a surface. We'll get to that. Start with the primary movement or particle drift. Lots of different names for the same thing. If you were here in person, if I were there with you, I would ask you, what is the traditional view of particle drift? And I'm hoping in your head you're all saying, little droplets plus wind equals bad. And that's what we've always said. Small droplets encounter windy conditions and they blow off course. We get it. But I want to flip the script a little bit because I think it vilifies wind. And I think, with the exception of obviously really strong wind, wind is not necessarily a bad thing. So let's do a little experiment. Let's say I handed you a golf ball and a ping pong ball. I've been doing this for years, so if you've heard this, I apologize. If you haven't, you're in for a treat. Imagine the golf ball is an extremely coarse droplet. It's got a lot of mass. It is heavy. Imagine the ping pong ball is a finer, smaller, lighter, more buoyant droplet. What I'm trying to get at here is that droplet size means changes in droplet behavior and how they respond to conditions around them. And to prove that, I'll ask, what would happen if I gave you both of these balls and had you turn into the wind and just chuck them? What do you think would happen? Well, if you've lived on the planet a little while, I hope you would say, well, the golf ball would kind of arc up in the direction you threw it, and then because of friction and gravity would fall to the ground, maybe roll a little bit, but you could pretty much predict what was going to happen to the coarser droplet. Now, the ping pong ball, having done this live many times, goes, I don't know, wherever. It's much lighter. It's much more influential, or sorry, able to be influenced by the world around it. So wind, convection, how hard you threw it, any number of things would change where it goes. So let's say I gave them back to you. And I said, okay, this time, really haul off and give her. What would happen then? Well, you'd never see the golf ball again. Even with my poor throwing abilities, I bet you I could get it to go a lot further. But it would still move in a straight line, and it would still, land in a predictable way unless it hit something and bounced. Thanks, Newton. But the fine, you might be surprised to discover, does something completely different. Maybe it ends up behind you. Maybe it does go a little further, but it doesn't move in a predictable way, and it certainly doesn't go a lot further based on the energy put into it. All droplets, based on their mass or size, behave differently. So now I'll make you choke a little bit by throwing you a great big table at you. This is generally bad practice, by the way, but we're going to focus in on a part of it. This entire table, its whole job is to model what different droplets do in different situations. Let's focus on two. This is a 50 micron droplet and a 200 micron droplet, or an extremely fine and, say, knocking on the door of a medium droplet. How long would it take for those to fall if I were somehow able to drop them from 3 meters? Well, the finer droplet, the extremely fine at 50 microns, would take 40 seconds to fall 3 meters, whereas the heavier droplet would plummet in 4 seconds. Well, what does that mean? Well, let's put a little crosswind in the equation. Let's say we've got a 5 km/h wind. That is not unreasonable. You might not even notice 5 clicks. While it's falling, that fine has the potential to move with the wind 53 meters before it hits the ground. But because it's falling faster, the larger droplet will only move about 6. This is a bit of a lie. Droplets evaporate. Other things affect them depending on how dry they are, what they're made of. So it's a bit of a fluffy example. In fact, that superfine droplet in the real world wouldn't exist even for 5 seconds. It would just go whoop and evaporate into a little dust mote, which, believe it or not, means it can go a heck of a lot further because now it's even lighter. Whereas the larger droplet has a better survivability. It could live for up to 30 seconds, long after it hit its target before it evaporated, which is what, as spray operators, we want. We want the droplet to survive long enough to get to where it's going. So let's reconsider wind and its role in drift based on this new information. Knowing this, what would you say is now the cause of primary movement or drift? I would suggest that something that has a low energy state, say a superfine droplet, gets exposed to some outside force. Wind, an obstacle, thermal, I don't know, turbulence. And as a result, it moves. So who's the villain here? Is it wind, or droplet size, or something else? Well, knowing now how this relationship works, what can you do to keep your droplet on course and out of your neighbor's hair? You could raise that energy. We could give the droplet more energy. Well, how do we do that? Make it bigger. Use a coarser droplet size. Speed it up. Reduce the amount of time that it's exposed to outside forces and get it where it needs to go before it moves off course. And you can do that with low drift nozzles, like air induction nozzles that tend to make droplets coarser, or you could use something like air assist, a technology that blows the droplet where it needs to go, speeds it up, helps fight outside forces. Or maybe you reduce the exposure of that droplet to some outside force. You can protect it, or you can decrease the amount of time that it is exposed to some force, or maybe reduce the equipment force and how it's acting on it. Let me explain. Shrouds. Shrouds will protect a droplet from wind. Shrouds are also a bit of a pain in the butt, but we'll talk about that too. You can reduce the distance to target. Well, maybe I get my nozzle closer to where I need the droplet to go, lowering your boom. Maybe I slow down. The actual act of the sprayer moving through air creates turbulence behind it. That's an equipment force. And if you slow down, you reduce that amount of turbulence, and that's one less force acting on the droplet. And in the case of using air, and this is more of an air blast conversation, I would say you should be using the right kind of air and the right amount of air. That's a bit further than we need to go. Let's talk about droplet size, nozzles, and pressure. I'm going to step back and just drop a little basics on you here. When we talk about a nozzle, we say get a medium, get a coarse, get an extremely coarse. It's a bit misleading because most growers might think, well, if I've got a nozzle that creates a coarse droplet, that's all it makes, just coarse droplets. And it gives you a sense of being a little bulletproof, and that's not necessarily correct. All hydraulic nozzles, no matter how they're rated, medium, coarse, extremely coarse, whatever, produce a range of droplet sizes. This graph here is volume median diameter. All that means is how much of the liquid that my nozzle is producing is comprised of smaller droplets, moderately sized droplets, or very, very large droplets. And the vast majority fall in the volume median diameter. Most of the liquid coming out of my nozzle is comprised of bigger droplets. And even this might suggest to you, well, look, it's only a little bit that's tiny. And likewise, it's only a little bit that's huge. Predominantly, the droplets coming out of this thing are of a certain size. But like I said, that's kind of misleading. Let me show you this. This is a medium nozzle. You'll see that the coarser droplets end up at the horns on the outside, and they're moving pretty quick. Look at where the fines are. They're in the middle. They're moving a lot slower, just like we talked about with the golf ball and the ping pong ball. One nozzle producing a variety of droplets. Now, even though this is medium, does this make you feel comfortable that they're all medium? Nope. This is also, by the way, why we want 100% overlap between nozzles. We want the coarse from the next nozzle, the edge of that spray pattern, to fill in that fine bit in the middle. If I were to look at what's coming out of that nozzle a little differently, instead of saying how much volume is made up of droplets of a certain size, let's just, because that's confusing, let's just count the droplets that come out of this thing and then sort them by size. This is a droplet size distribution. And this, by the way, is the exact same nozzle as this. This looks good. This raises questions. In fact, there's the water sensitive paper I used to calculate this. In this case, you'll see that, the number of droplets that are less than 200 microns, if you count them, they're on the left side of this histogram. There are a lot of them, and fewer and fewer and fewer large droplets. And this is because of the cubic relationship between volume and droplet size. If I were to take a droplet of a certain size and say, okay, how much volume do I have there to make droplets of half that size? You'd have 8 times as many droplets. But let's not go down that rabbit hole. You get a lot more fines than you realize. So the point of all this is, even if you're using a nozzle that produces a coarser droplet size, they're not all coarse. You're not bulletproof. Nozzle manufacturers will voluntarily provide that size, and we're seeing increasingly more and more labels saying use a coarse, use an extremely coarse, use an ultra coarse. There's no reason I can think of in a broad acre application for anyone to be using the low end of medium or finer. Not for a fungicide application, not for anything. It's just a great way to create a drift situation and frankly, not do yourself any favors in the coverage department either. You should be using the high end of medium, even for a fungicide application, or the low end of coarse and above. Okay, how you use your sprayer and how you set up your sprayer also play a role in drift. Let's get this out of the way. The best way to mitigate drift is just not to do it in the first place. And I heard some great speakers talk about this. They did studies on the terrible smell that comes out of chicken operations and how do we deal with neighbor complaints about bad smells. And they modeled it for 3 years, and they did real life practice. They did real life setups, putting hedgerows and things in the way of these chicken operations. And they said, ultimately, it did help. Just as cedar hedgerows do help with drift in a limited sense. But the best thing to do is just not do it in the first place. Why try to stuff that cat back in the bag? Just don't let it out. I own a cat. Don't be offended. High speeds and high booms go hand in hand. We know that the linkages on our booms are such that if you're in hilly terrain, like we often are here in Ontario, you might smack that outside section. So we raise our booms. And the faster we go, the more sway and yaw we have to deal with, so the higher the booms go. And the higher the boom, the more opportunity for a droplet to get affected by outside forces, right? This picture is not typical, but this is in Western Canada. This operator is going at 25 miles an hour. Do you see what happens to the spray behind a sprayer when you speed up? The sprayer itself creates turbulence. The droplets are in the air longer because they have further to fall. And there may even be a shear effect where they tend to get smaller. So all in all, not a great way to go. Your equipment creates that turbulence. We'll talk about this in a second. But here's a fun fact. If I ask an audience, would you spray in a 5-kilometer-an-hour wind? Every hand goes up. How about 10? I got to get it done. That doesn't seem too bad. Most labels don't say anything bad about 10. How about 15 kilometers an hour? Whoa. Depends what I'm spraying, depends on who's downwind. All decent answers. Would you drive 15 kilometers an hour into a 15-kilometer-an-hour wind? That tends to drop a few hands because they're not sure where I'm going with it. What you get is something called apparent wind speed. The droplet experiences the additive impact of how fast you're going plus the oncoming wind. So essentially, it's a 30-kilometer-an-hour wind. It adds up. And when that happens, that sprayer acts almost like a speedboat in the water. It creates turbulence behind it. Perhaps that sucks fines right out of the swath. Or maybe, as I mentioned, it can create a shear condition. Generally, it makes it unpredictable, and we don't like it. And the bigger the boom and the bigger the chassis, the worse it is. Tom Wolfe did this work a couple of years ago with PAMI, and they just wanted to kind of see what is the consistency of where droplets land under the boom. So they took a sprayer and a sampling mechanism, and they sprayed a dye, and they put the sprayer in a condition that isn't ideal. High boom, fast speed, and medium droplets, so relatively small. And then they sampled how much spray was under the sprayer based on what they expected. Ideally, you want 100% of the spray to land under the boom. That reality is different. So they looked at it and went, ooh, our coefficient of variance is 38%. In other words, there is a 38% variability in this. And you can see from this graph that it's depressed right around the wheels and the chassis. The actual sprayer itself was creating turbulence that was whipping all the spray out from under the swath. This is not a good thing. You don't want to find out that you're right 62% of the time. So they adjusted the sprayer, and they did what we've all told you to do for years: go low and slow. So here's a lower boom, slower speed, again, medium droplets. Unfortunately, not a huge improvement, some improvement, but still pretty variegated as a result of the sprayer itself, swimming like a fish through water. So what this tells us is, even though low and slow is the way to go, the sprayer itself, that design, if it were a bit more streamlined, perhaps, some consideration as to how the wheels are fendered, maybe some way to make it slipstream, may improve matters for deposit variability. But certainly low and slow did help. You don't like the idea of slowing down. I get that. Maybe consider a longer boom, but be aware that that also introduces weight and leveling issues. This is sort of a great white whale for Tom. He spends his time standing in front of oncoming sprayers, risking life and limb in the hopes of getting a shot with the boom perfectly level. So far, not so much. Just in the matter of moments between these two photographs, you can see the cant where one side goes down and one goes up. And that's even with auto levelers. Higher travel speeds will always make your boom sway. And if it's drifting, then it's not where you want it to be. This histogram, also developed by Tom, shows how different situations may or may not improve how much spray is landing under your boom. For example, these two bars on the left, this is the percent of what they expected to find under the boom. Just think of it as coverage when the boom was low and they were traveling slow. And on the right, fine, medium, and extremely coarse droplets, high boom and fast speed. And on average, just slowing down and dropping your boom, and 10% more product landed where it was supposed to land. So, it's the flip side of the same coin. If it didn't drift away, then it landed where it was supposed to, and vice versa. Maybe just going to a coarser spray is sufficient. I still want to drive fast with a high boom. You haven't convinced me. Can't I just increase droplet size? It helps, but again, there's only so much just the droplet size can do. More work by Tom, who I guess I should be paying money to use his slides, but at least I'm acknowledging him. This is how much drift Tom and his team found 5 meters downwind of certain situations. So on the x-axis, this is how windy it was that day. On the y-axis, that's straight up and down, how much drift happened. So here the sprayer used a turbo T-jet, an 05, 110 degrees, and the boom was kind of high, 30 inches. Just by changing to an air induction, I guess this is an 04, but basically the boom's the same height, wind conditions are the same. All we did was go to a coarser droplet. Look how much less drift there is 5 meters downwind at any wind speed. If we look at 14-mile-an-hour wind, then we see that just switching to air induction dropped drift twofold. You're half. Maybe we can do better. Let's use that same nozzle, but now let's drop the boom as well. Well, just because it's nice round numbers, let's look back at 8 miles an hour. What this means is by increasing to a coarser droplet size, big impact, but by also dropping your boom, 4-fold reduction. That's awesome. And it stands to reason that where did the spray go? Well, it didn't blow away. It landed under the boom where I wanted it. So getting your boom height right and your nozzle spacing right improves your coverage uniformity and reduces drift. We sprayed fluorescent dye in the snow because we have too much time on our hands, and you can see the result. Spraying at the right height means consistent coverage, and this was a super windy day, so there was still some drift. We get too low, we get striping. We don't get the overlap, and frankly, it was so windy that the drift wasn't affected a ton. Probably had some bounce in there, but look what happens when the boom's too high. Inconsistent coverage. In fact, it stripes in the other direction. So low and slow is the way to go, and I don't recommend spraying in the snow. Drift reducing tech. Maybe there's something you can buy or add to your sprayer to help matters. You can get shrouds. I mentioned them earlier, and I know a lot of horticultural operations that use shrouds on their sprays. They work great, especially with banded applications where you're trying to get them between the rows. But as an overall solution, I've never seen anybody with a full set of shrouds on a field sprayer. Maybe I'm not caffeinated enough. They're heavy. They cause a lot of drag, and we've seen what turbulence does, even though you have protected the droplet from that turbulence. But it makes the boom heavy, and it affects your weight, and there's drag. And worst of all, you can't tell if you've got a plug nozzle. So not my favorite way to go. But if you're in a real hard situation, they can do the trick. I still love air assist. I don't know why North America hasn't glommed onto it. Admittedly, we don't have a lot of self-propelled sprayer options with air assist. But if we ever pulled the trigger on that, I think we'd be rewarded. You can see on the left with this hardy pull behind, the wind was going from right to left, and we didn't use air assist. And then we turned on air assist, which creates a curtain or a shroud of air. That's on the right, and it kind of blows into the direction of travel. And all of that drift moving downwind stopped. In fact, it starts to blow into the direction of travel. You can see some curls there. And that air assist does a lot of stuff. It expands your window. So if it's a little too windy to spray conventionally, maybe you can compete with that by using your own air. It opens up a canopy and delivers the spray into it, where normally a droplet would never penetrate. Perhaps the air, the mechanical energy of the air can open that canopy and deposit the spray inside. Super for fungicides. Lots of great reasons to use it. Well, I don't need any of that. I'm just going to throw some adjuvants in the tank and we're good to go. Please don't do that. Adjuvants do work. Lots of data demonstrating that. Some work far better than others. I just happened to pick interlock for this, but I could have used anything, I suppose. The point of this is adding an adjuvant, a drift reducing adjuvant to your tank is the last thing you do. You deal with the weather, you deal with your mechanical technologies, you deal with how you're using the sprayer, boom height, travel speed, droplet size. Do all that first. And this is the sprinkle on the donut. It is not the first thing you do. it's the last. Okay, we're doing well. Secondary movement. We've talked all about primary drift, the stuff that I think we all intuitively know about. Let's talk for a moment about secondary movement or volatility. What is it? Ask somebody, you'll get a different answer, but let's do this. Some chemicals are just by their very molecular properties inherently volatile, and you drink one every day, I hope. Water is a great example of a volatile. It can go from a solid to a gas. When you add heat, it evaporates. That's volatility. It does it all by itself. Now, admittedly, the hotter it gets, the faster it happens, and that's a property of volatility. When we first reintroduced, I say we, when dicamba was first reintroduced, Ontario was waiting for the new formulations. We did well. We didn't get a whole lot of off-target drift complaints, and I'd like to think that was because we spent a number of years educating operators on what to do and what not to do. But it really knocked us out when, in those early days, the southwestern U.S., no, that's not true. Well, the southern U.S. had so much trouble with off-target drift volatility from these dicamba formulations. And Mike Kober did something so clever. He thought maybe it's just plain old temperature. Maybe we got lucky that our temperatures aren't as hot when we apply this. So we took a look. And this histogram is Mike looking at the temperatures in Elora and the temperatures in Little Rock, Arkansas on the same day of the same year, 2016. And in May, there was one day in Elora where it was, according to the label, too hot to spray, where volatility would have been a really big deal. And in Arkansas, there were 6 days you couldn't spray. In June, well, Elora only had 2 days where it was so hot that you couldn't spray. Arkansas was at a lot 24 days that month. And in July, hang your sprayers up in Arkansas because every day was too hot to use a volatile. And in Elora, there were 5. So anyone looking for a warm place to go for the summer, go check out Arkansas. But your environmental conditions are definitely a factor in volatility. And admittedly, these products are a lot less volatile than they used to be. They're not no volatility. Don't believe that for a second. But Banville Original, if we call that 100% volatility, whatever it was, that's the worst case scenario. Banville 2 tipped in at about 25% as volatile. And the Ingenia formulations and the new formulations of dicamba today, they're like 25% of that. But the point of this is they're not volatile, to use the double negative. There's still some concern. And you think, well, all right, so only a little bit gets away, big deal. Well, it is a big deal because some of these synthetic oxins, including 2,4-D, which is less volatile but is still pretty potent, it just doesn't take much to cause trouble, especially on perennial horticulture crops. If tomatoes looked sideways at this, they'd curl up. Grapes too. Imagine taking 1 cup, like a measuring cup, of field strength dicamba out of a 1,200-gallon tank. If you were to somehow manage to spread that, like put it in another sprayer and spray it out, you would definitely upset conventional soybean. Wouldn't necessarily cause yield loss, but there'd be visual damage. If somehow you managed to carry 2 gallons of dicamba at field strength into another field, you would get significant yield loss. And it's even worse if the crop is at a particularly susceptible stage. For example, we know flowering soybean is very unforgiving when it comes to a whiff of dicamba. So it's the volatility, of course, but also the potency of what you're spraying that's moving that can really cause chaos. Again, at a demo, Mike Kober and I did this. This was his idea. The pop jug on the left, let's say that represents a full sprayer, however much liquid that is. Now, let's say you accidentally carried 33% of that volume with you and it was Callisto, and then you sprayed a non-trait soybean. You'd get 10% yield loss. You'd have to somehow lose your mind and forget you had 1/3 of a tank of Callisto in there when you sprayed conventional soybean. It's less forgiving with Roundup. You'd only need 6% of whatever was in your tank to cause that damage. But for dicamba, in this case XtendiMax, you would need 0.16 of whatever was in your tank to cause damage. You can just see the little dribble of liquid at the very bottom of that pop bottle. And I confess, that's an exaggeration. We needed so little volume that people were looking at the pop bottle and they weren't seeing any liquid in it, and they thought we forgot to fill it. So we just threw a few drops in there to make it look like something was in there. It doesn't take a lot. So now, knowing that product choice is the big problem with volatility, if you chose to spray it, what happens happens. How can you hedge your bets a little bit? And that leads us to atmospheric stability. This is me going back to saying wind is not the villain here. If you spray on a moderately windy day, let's just say a light breeze, yeah, it's going to increase the potential for physical drift, but you know which direction it's moving. And because of convection and dispersal, these thermal mechanical methods of spreading spray out, it tends to reduce the impact. So we know which way it's going, and we know it's expanding quickly in 3 dimensions. So whatever arrives, as long as it isn't something super potent, will help reduce the impact. It can help us plan if we spray on a lightly windy day and we know what's downwind. But what if we can't predict where it's going? We're going to talk about inversions now. This picture is kind of the typical state of affairs on any given day. Cold air, in this case blue, sinks, and warm air rises. It's why hot air balloons go up, and it's how lava lamps work. In an inversion, you end up with a topsy-turvy sort of situation. The warmer air is on top, and the cooler air is below. And cooler air doesn't want to go up, and hot air doesn't want to fall down. They don't layer, that's technically incorrect, but relative to one another, you get this kind of ceiling. And if you're spraying back and forth in a field, and you're in a cool inversion situation, anything that stays in the air, like those superfine droplets or volatile products, they don't go anywhere. They can't disperse. There's no mechanical energy to get them to go up. All they can do is just hang there. And we know it takes forever for them to fall. But they do go somewhere. Air is sort of like water. So if it's kind of a calm condition and you're in an inversion where you're spraying in that cool layer, air will move like water. It'll slowly move downhill. It's why we see things like fog in ditches. It's colder in there, so the water condenses. Which way is it going to move? Do you know your topography? Do you know which way is downhill? You might. Or maybe what happens in the lightest of breezes? Don't know. When does this terrible thing happen? It's not a terrible thing, but you need to be aware of it. And it tends to happen to some degree almost every night. Not every summer night and not as intensely, but depending where you are, they're going to form more often than not. As a generality, when the sun starts to go down, the Earth's surface starts to cool and an inversion can start to form. It gets more and more intense, or that ceiling gets higher and higher through the night until the sun comes out the next day, wind picks up, you start to get that mechanical churning of the atmosphere, and the inversion burns off. So if you're a night sprayer, you might be spraying in inversions. And what can that possibly look like? Richard Anderson, and I think his student at the time, Hope Long, did this wonderful video in 2017 in Thamesville where they dropped a smoke bomb and just wanted to see where the smoke, a surrogate for vapor, would move in an inversion. So they strapped it to the back of a sprayer and did this. I'm going to show you a sped up video from those guys. This is 90 seconds of smoke. That's how long these bombs go off. The wind was almost dead calm, 1.2 miles an hour. And what you're about to see is a 52-minute video compressed. Just watch and think about what you're seeing. That 1.2 mile an hour wind seems to be going from the right of the screen to the left. Here they come back, they're empty. See how they drove through the fog and just churned it around? It's not really going anywhere. That phenomenally light wind is slowly pushing it downwind off screen. And normally you would think, well, that's the end of the video. Wait a minute, what's this? It's back. And now it's moving from left to right and exits in the other direction. This took an hour. So in summary, you could have chosen a situation where you knew which way the wind was blowing and you knew that the downwind direction was relatively safe for drift. You know, there was nothing there that required a particular protection. But because you sprayed in a pretty calm condition during an inversion, by the time you left the field, whatever was hanging in the air actually exited in the exact opposite direction It was moving when you started. What are you going to do about that? Well, don't spray in an inversion. Now, I know smoke particles aren't vapor, but it's a pretty good surrogate. So how do you know when there's an inversion? There are a few cues. If you can hear distant sounds, things like, I don't know, if you've ever camped on a lake and you can hear somebody talking and it turns out they're half a kilometer away, sound will bend in an inversion. Smells will travel long distances too. So, that distant train in the night, that's probably in an inversion. And when you drive out that morning to spray, if the dust is hanging in the air and you can see where you came from, you're probably in an inversion. Humidity will slow an inversion's formation in the night. It actually, I won't get into it, but it interferes with how hot and cold will separate. If it's a cloudy night, that reflects radiation. It will also kind of reduce the impact of an inversion. And of course, wind. If you've got wind, it generally means you're not in an inversion. They tend to be concurrent with one another. So what does that mean? Spray on sunny days and a light breeze. That's where you can predict where everything's going and you're likely not in an inversion. And if all of that is confusing, just go to a weather forecast website. The companies that manufacture and sell synthetic oxidants, I won't say who or where, they have these websites you can go to and see if you're in an inversion or not. There's even some tools you can buy. One of the reasons inversions are particularly challenging in the case of drift, it's not what causes them. We're starting to get a pretty good idea of that. But after they happen, who gets fingered? Like, where does the blame go? And how could one person cause, so much chaos? I looked to Australia and cotton issues they were having with 2,4-D. This is Mary O'Brien. She goes by Spray Drift Girl, and she coined the phrase community drift, and I loved this. I'm not going to go into the math, even though I've got it here, but let's say one sprayer spraying a few fields is capable of putting 250 grams of active per acre into the air. I'm sorry, onto the ground. And some portion of that, 1% of what you sprayed, leaves the ground as a volatile, which means now 2.5 grams of active per acre is somewhere in the air. Is that enough to cause damage? Well, according to Mike and I in our pop bottles, not quite, but it could. But you sprayed 150 acres, not one. So the cumulative loading in the atmosphere is now 375 grams. That could totally cause trouble. And maybe it wasn't just you. Maybe all the neighbors are out spraying. That's 5 sprayers operating for 4 hours. Their collective impact on how much of this product could be in the air is 7.5 kilograms. And it takes 0.3 to cause visual injury to cotton. So some poor cotton grower gets burned and tries to find the person who sprayed the synthetic auxin. And who do they point to? The person that was closest, either in time or in space. They take the brunt of it, even though it was a community effort to load enough product into the air to cause trouble. So who's at fault? Kind of everybody, but because it's hard to figure out, probably the person that was closest. Dr. Kevin Bradley, in trying to explain this, once said, if you're going to use the traits, then you're going to spray the product. And if you spray the product, you're going to load the environment. And if you load the environment, you're going to get secondary drift, period. Controlling it, containing it, reducing it, very, very hard. Similarly, Dr. Tom Wolfe did some cool work. He said, we looked at how much drift came off a field. Usually that work is done off a couple of passes, but he warns that if you're not just doing a couple of passes, there's a cumulative impact of how much drift is released or the potential for drift with every pass. You've got to look at what happens when you spray the whole field. And in the case of an inversion and finer droplets or volatility, that adds up. Okay, you made it. Let's do the summary. I can't think of anybody better to quote than Tom, since I've plagiarized all of his work in this talk. Here he is exposing Micron Woman, the superhero that he is. Pesticides move in the atmosphere, but they're rapidly diluted by mechanical and thermal turbulence. A little light wind, a little convection on a sunny day. That's why we've said maybe the wind isn't the villain in all this. A light wind, a light breeze, it can move a product in a predictable direction, and it dilutes it rapidly. It grounds it or sends it up. We can minimize that particle drift, the one we all understand, by using lower booms, protective shields, slowing down, going to coarser sprays. And we avoid applying volatiles if we can. And if we have to, watch for inversions. just be very conscientious about those, figure out what they are. And those are that's the stable atmosphere we're trying to avoid. We do like the thermal conductivity, God, I'm tripping over my words now. We like turbulence, we like a light wind. If this was all too much, and of course it was, who could have followed all this? You should know that a number of groups have come together over the last year to develop a new website. It's called Be Drift Aware. In fact, it's a whole campaign to make operators and anybody aware of what causes drift, what to do if you suspect drift, how to mitigate drift. And because there's just so much information out there, what this website does is bring it all together in one spot and organize it in a more intuitive way so that you can look by subject for whatever it is you want to learn about. I want to stop drift. I want to know what might have caused it. I want to know what to do if I suspect it. So by going to bedriftaware.ca, all of this information is at your fingertips. There's even a quiz to test your knowledge, and I encourage you to go check it out. These groups worked pretty darn hard on it. And if you'd like to know more about spraying in general, there's more than drift. I propose you go to sprayers101.com, which is a resource that Tom and I developed, and it's got over 300 different articles, videos, downloadables, books, poetry, truly. Go there. You can learn anything you never wanted to know about drift, or reach out to either Tom or myself. So that's it. You survived. I don't know how long I talked for, but I'll hand it back to Laura.
Amazing. Thank you so much, Jason, for sharing your knowledge on drift. Every time I hear you speak, there's something new that I pick up, and I think that's pretty incredible that there's a lot to know on drift and on managing drift. And I really loved the golf ball and ping pong ball comparison. Like I've never seen that comparison before, and I thought it's something that you can so easily visualize and just kind of keep that in the back of your mind as everybody's headed out. What am I spraying? A golf ball or a ping pong ball? So a brief note as the webinar is coming to a close. For those in need of CU credits, please email myself at lfarrier@gfo.ca. But before we go, Jason, I do have a couple quick questions for you, just that I was thinking of throughout the webinar. So you were talking about apparent wind speed and how your travel speed and wind speed, of course, impact drift. What's a good system that operators could have that measures the wind speed while they're operating? So if all of a sudden that wind speed peaks or drops, is there something that exists like that?
I haven't got an easy answer for that. Some sprayers do come with weather monitoring systems. I haven't seen any myself. I think the best and most versatile tool an operator could invest in is a handheld wind monitor, like a Kestrel or something similar. So the idea there is you go out to the field, you hold that at boom height, and you get your wind reading. That localized reading is so much more accurate than any nearby tower that they're using for the mesonet for weather. And if you suspect conditions have changed, and just look around, you can see air moving through the field. You can watch treetops, snapping flags, smoke. Back in the day, they used to say, burn a tire and see if you're in an inversion. Please don't go out and burn tires. I don't know who would have advocated for that. But being aware of the environment around you when you're suspicious in your insulated, air-conditioned, vibrating seat cab, maybe it's worth a second to get out, have another look. And as I say, the most versatile thing I can suggest, the most applicable things are those handheld Kestrels. And write it down, like put it right on your spray record. If you don't have one of those, go to your phone, go to one of those mesonet weather systems, and you can see the direction of there's no actual phone here. I'm pantomiming. You can see the actual direction of wind. Take a screenshot. Now it's time-stamped, and you'll be able to say at this point of time, at this location, this was the weather. And do a shoulder check. If you see spray whipping up behind you, conditions might have changed. Just be aware. Be part of the situation you're in. It's really easy to get insulated and become, as Helmut Spicer used to say, a sprayer jockey rather than a sprayer operator.
Those are great suggestions. Thanks so much. So right now when we're filming this, it's the middle of May. We've been battling a lot of wet fields, and then when the ground is kind of fit to go, it seems the wind speeds are up quite a bit. So what are your suggestions for sprayer operators when they're in these situations where it's go time and
Yeah,
it should be applied, but we've got maybe some conflicting conditions that maybe aren't. What would you suggest and say to them?
it's not easy. I mean, I know it's not easy. We all know it's not easy. And I did mention some drift mitigating practices, but they do tend to nip away at productivity. The idea of driving slower to mitigate drift adds more time to how long it takes to spray, when, as you said, you're already pressed for time. Rain just left, rain's coming, I gotta go. There are other ways to claw back that productivity, taking unfortunately, it's not the kind of thing you can do in the heat of the moment. You have to prepare ahead of time. But just a sharp pencil and a stopwatch to time how long it takes to do certain things in your practice. How long does it take to tender? How long does it take to fill? How long does it take even for my boom to open up? What what does it take throughout the day to get the entire day done? Does speeding up actually make sense to do things faster, or should I rinse faster, clean faster, fill faster? Have a critical look at that, and then maybe it'll be an easier pill to swallow if slowing down is the best move. Another trick, carry a larger, coarser nozzle on your sprayer. Maybe you're doing a fungicide and you think, I want something that's medium coarse. That would be ideal at this volume, but the wind's picked up. I've got one tank left to put on. I got to get it done. Maybe then you start to compromise coverage potentially a little bit by swapping on the boom to the larger droplet size. Now you are probably going to put out more volume and more product because you haven't changed your spray mix. You could adjust your pressure or your rate, maybe not, but going to the larger droplet size will reduce the potential for drift, maybe at the expense of coverage, but it's a lesser of two evils decision. You've got to be in the moment and be situation aware to look around and go, who's downwind, what's downwind, know what I'm spraying, know what it could do, know how the product works, and does it warrant speeding up, slowing down, changing to a larger droplet size. But give yourself options. Be prepared, have those nozzles on the sprayer, and be prepared to go to that larger droplet. Know how long it takes for all those little activities, and know what may have to be sacrificed to get the product on and what the potential impact of that is. See, it's not an easy answer, but
Never is.
you can't use ignorance as a shield. You can't say, I didn't know that I wasn't supposed to drive like crazy with the boom up in the air. Be drift aware is going to show you that's a bad idea. And there are some articles on there that do make these suggestions. Maybe speed your fill time up so that you can slow down and do a better job. Maybe have those larger spray qualities on your sprayer and be able to move between them as the situation requires. But unfortunately, there are going to be those times where it's too risky. You're on the downwind side of a field and you've got a sensitive area or sensitive crop right next door. Don't do it. Don't do it. It's not worth it. It will always come back and bite you.
That's all great suggestions. I also loved how you said to look at your operation, maybe not when you're swamped, but where is those time sucks that you're washing jugs or whatever. And I
Yeah.
know I attended the Spray Smart conference earlier this year, and there was a number of operators who were speaking that day who were talking about how they've made their operations more efficient for days and times like this where we are really crunched for time. And there's a lot of resources in Ontario and a lot of incredibly innovative engineers who are making these new systems or different ways of doing things to help speed them up on that downtime when they are loading, and just to speed that up so that they can get more acres in a day for those good spray days. So yeah, I really appreciate your time today, Jason. Spectacular learning, and we just appreciate you taking the time.
My pleasure, Laura. I hope when this airs, people are having a nice drift-free season.
I sure hope so too. Thank you.